Welcome to EDU World Space.
Here in this problem, we have a rough diagram of a cable that is 50 feet long and it is suspended between 2 points that has a length of 15 feet. They tell us that the minimum tension is 200 pounds and they want us to find the total weight of the cable as well as the maximum tension. Now for starters, we're going to establish our origin and coordinates, which will be directly at the center of the cable, where X is going to the right and Y is going directly up. Now, because they gave us the minimum tension, we can therefore use this equation, T times cosine theta equals F sub H, in order to essentially solve for that variable. Now, you have to remember that F sub H is the horizontal component of the tensile force at any point along the cable. It's also important to remember that the maximum tension occurs at the supports, while the minimum tension occurs at the center of the cable. And because our origin is also at the center of the cable, we can therefore say that that angle is 0. So when we plug in those values, we get that 200 pounds times the cosine of the angle of 0 equals 200 pounds for that variable F sub H. Now that we've solved for f of h, we can now derive the hyperbolic equation that defines the shape of the cable, which will then lead us to the value for the weight per unit length. Now, the equation that defines the shape of the cable is defined by x equaling the integral of ds all over the square root of 1 plus 1 over f sub h squared times the integral of w as a function of s times ds squared. Now, if we replace ws with the variable w and take the first integral, underlined in red, our x equation then becomes x equals the integral of ds over the square root of 1 plus 1 over f sub h squared times w times s plus c1 squared. And the reason that we have a c1 in there is because we aren't evaluating any of these integrals with numerical values. So therefore, we need to have a constant in there. Now, if we go ahead and take the integral of this equation using u substitution, u is going to be 1 over f sub h times w times s plus c1. And when we take the derivative of that, we will have du equals w over f sub h times ds. And when we solve for ds, we get that ds equals f sub h over w times du. And now that we have all these variables, we can go ahead and plug this into the original equation and continue to solve. Our deflection curve equation then becomes x equals the integral of f sub h over w, because we are substituting in ds, all over the square root of 1 plus u squared du. The integral for this function looks a lot like the integrals that are used for trig functions. In fact, the answer to this is the inverse hyperbolic sine of x over a plus c. So our equation then becomes x equals f sub h over w times the inverse hyperbolic sine h of 1 over f sub h times w times s plus c1, all of that in parentheses, plus c2. Now that we have this equation, we need to go ahead and solve for constants c1 and c2. And in order to do that, we are going to do the boundary constraints. And those constraints in this case will be s equals 0 when x equals 0 for the original equation. And when you take the derivative, it will be dy over dx equals 0 again when s equals 0. Now, instead of using the first boundary constraints, I'm going to go ahead and use the second one. And we can't use our deflection curve equation because it does not have a variable y, therefore we cannot take a derivative. But you have to remember that in this section, we were given the equation of dy over dx equaling to 1 over f sub h times the integral of w as a function of s times ds. When you take the integral of that equation, you get that dy over dx equals 1 over f sub h times w times s plus c1. So if we plug in our boundary constraints replacing dy of dx, that will be 0, plugging in 0 for s. And if you solve for c1, that equals 0. Now if you plug this constant as well as the other constraints back into the original x equation, you'll have that 0 equals f sub h over w times the inverse of the hyperbolic sine times 1 over f sub h times w times 0 plus 0, because c1 equals 0, all in parentheses plus c2, and you solve for c2, you'll also get that that constant equals 0, leaving us with the final equation of x equaling f sub h over w times the hyperbolic sine, the inverse of the hyperbolic sine of 1 over f sub h times s times w times s. Now what we want to do is we actually want to solve for s in this case, because once we do that, we are able to plug in all of our known values in order to solve for w. If we solve for s by multiplying w to the other side and dividing by f sub h, we get that w times x over f sub h equals the inverse of the hyperbolic sine of 1 over f sub h times w times s. And if we multiply by the hyperbolic sine on each side, our equation will be hyperbolic sine of w times x over f sub h equals the hyperbolic sine times the inverse of the hyperbolic sine of 1 over f sub h times w times s, giving us hyperbolic sine w times x over f sub h equals 1 over f sub h times w times s. And by finally solving for s, our equation then becomes s equals f sub h over w times the hyperbolic sine of w times x over f sub h. By evaluating this equation at the origin from one end of the cable where s equals 25 feet and where x equals half the length between the 2 points, which is 7.5 feet, and where f sub h equals 200 pounds, which is exactly what we solved for earlier, our new equation is 25 feet equals 200 pounds over w times the hyperbolic sine of w times 7.5 feet over 200 pounds. Now, instead of solving this by hand, I would highly recommend that you solve this using a graphing calculator to solve for w, where you plot the left and the right hand side, and you find where the lines intersect one another. Now, if you don't know where to find the hyperbolic sine on your calculator, if you're using a TI-83 or 84, then you need to hit the second catalog, which is directly above the zero, hit the natural log button, which is where S is. It'll take you to the S section, and you'll scroll all the way down until you find the hyperbolic sine. Now, when you find when the 2 points intersect one another, W comes out to be 79.93 pounds per feet. Now, this is the weight per unit length, but they want you to find the total weight of the cable. And in order to do that, you need to multiply this by the length of the cable, which is 50 feet. So the total weight of the cable equals 3,996.5 pounds. And if you want to convert this to kips, just remember that 1 kip is equivalent to 1,000 pounds, which is equal to the total weight WT over the weight that we solved for earlier, which is 3,996.5 pounds. And the total weight in kips is approximately 4. So depending on the answer in the back of your book, it'll either be in pounds or it will be in kips. And now that we solved for the total weight of the cable, we're going to find the maximum angle, which will allow us to solve for the maximum tension. To solve for the maximum angle, recall that dy over dx equals tangent theta, and that our deflection curve equation was S equaled F sub h over W times the hyperbolic sine of W times X over F sub h. Now, because we don't have a function of y, but we instead have a function of s, we need to replace that dy over dx with ds over dx, which will allow us to take the derivative of this equation. So when we do that, we get that ds over dx, which will be evaluated when x equals 7.5 feet, equals the hyperbolic sine of wx over f sub h, which also equals tangent theta. So when we plug in our known values for wx and f sub h and take the inverse tangent of the left-hand side, theta max will be equal to the inverse tangent of the hyperbolic sine times 79.93 pounds per feet times 7.5 feet over 200 pounds. And the angle that you get will be 84.28 degrees. Now with this known angle, we can go back to this equation. T times cosine theta equals F sub h to solve for the maximum tension. So T max will equal 200 pounds divided by cosine of the angle 84.28 degrees, which will give us a maximum tension of 2,006.68 pounds. And if you want to solve for kips, remember that 1 kip is equivalent to 1,000 pounds. And we're going to say that that equals Tm for Tmax over the weight that we just solved for, 2,006.68 pounds, giving us a maximum tension in kips to be 2.01. So depending on the answer in the back of your book, your maximum tension might be in pounds or it might be in kips. And to conclude, as the problem was asking, we know that the total weight of the cable was 3,996.5 pounds, and that the maximum tension was 2,006.68 pounds. And that is exactly how you solve this problem I hope it helped.